If a changing magnetic field can create an electric field, can a changing electric field create a magnetic field? We're going to answer that in this video here. And we're going to start with a correction, a problem to Ampere's law. I've got a figure here that I've copied a few times. I'm going to need it a few times. And in this figure, we're going to suppose that we have a current carrying wire and I is time dependent, so it's alternating. And then we have a capacitor. And a capacitor, as we know, is a kind of a break in this current, but it's got an electric field E, and we're going to say that the capacitor is a parallel plate capacitor with a circular radius R. So this is our setup. Okay, I'm going to illustrate the problem of Ampere's law as it is right now. Now we know that the electric field in that capacitor is Q over E0 times the surface area of one of the plates of the capacitor. We looked at this when we talked about capacitors. And again, if each plate is a circular, if each plate is a disk, so it's circular and it's got a radius r, then we can write S as pi r squared, of course, right? Now, since remember the current is a change in charge with respect to time, then if we took the derivative of our electric field here, we would have dE of t is equal to, then we'd have dq of t. Everything else here is constant, so dq of t, dq dt is I, and then over all those constants, right? Okay, so this is something we're going to need towards the end of this video, so we're just going to put a box around it for now because we're going to have to recall it. Now, for our setup in this top left figure, let's say that we have a point P1 that is far away from the capacitor and above the wire. So maybe here is point P1. And let us say that we have a point P2 that is the same distance away from the wire, but it is closer to the capacitor. In fact, it's right over the capacitor. Let me label that P2 over here. Now let's go to P1. So P1 and P2 are equal distance away from the wire. Now going to P1, if P1 is far away from the capacitor, Ampere's law should give the correct magnetic field. So we're just going to consider that what this magnetic field is at that point. We're going to say it's a distance r away from the wire, so P2 is also a distance r away. At P2, though, there is an interruption of current. So in this gap in the capacitor, and so you may expect the magnetic field at point P2 to be a little less than P1. Remember that this current carrying wire creates a magnetic field that's swirling around, right? And so you might consider the magnetic field at P2 is going to be a little bit smaller just because of this gap in current, but otherwise it should be very similar to the magnetic field at P1 because the current is here and the current is here and it's swirling around. All right. Well, we can use Ampere's law or so it seems, to calculate that magnetic field. So with Ampere's law, recall that we have to choose an Amperian path. And so we will choose a circle. Because we know that the magnetic field is swirling around, we're going to choose a circle that passes through point P1, like that. And that is our closed loop L, right? And so from Ampere's law, we have the circulation of the magnetic field intensity around L is equal to the current that penetrates the surface through that closed loop. So the current that penetrates that circle is I, of course. So we've played this game before. We know that H is we've chosen a correct Amperian path, and so we can pull out H because it's parallel to our Amperian path everywhere. Right, so now we have this. And we can, of course, substitute, if this is in free space, that B is equal to mu 0 times H. And what we see is that the magnetic field, magnetic flux density, then is mu 0 I over 2 pi r, like that. So that's the magnetic flux density at point P1. All right, that was simple enough, so let's just repeat that at point P2. And so we again choose an Amperian path that's circular, right? So that's L. And we repeat this exercise and we say, okay, Ampere's law, the circulation of H around L is equal to the current that penetrates that surface, that circle. Well, I don't have any current that penetrates that circle. So this must mean that it's zero. And then, of course, this would imply that the magnetic flux density is zero. That's absurd, right? I mean, come on. You mean to tell me that the magnetic field is going to be, of some substance here, but then automatically zero right there? It just drops off to zero instantaneously? No way. That's absurd. All right. And in fact, we can make the situation much worse now if we consider a different surface. So let's go back to P1. I'm just going to even more emphasize how absurd this is. So I'm going to bring this figure up a little bit. Let's go back to P1, and we say we've got the magnetic flux density at P1, right? And so I'm just going to draw P1 again there. And I'm going to choose a different Amperian path here. And I'm going to choose this path, kind of with an open top like this, and a flat bottom. So now, nowhere through this open surface is the current penetrating. Right, so I'm saying it's got an open top there, and then the bottom is closed. So there's no penetrating current here. So now we would calculate the magnetic flux density at P1 to be zero. Well, that's equally absurd, right? Because we just calculated the magnetic flux density to be this thing. So this is an issue that needs to be resolved. And Maxwell suggested that we amend Ampere's law. And he asked, what is so special about the region in between the capacitor plates? And the answer is that there is a changing electric field in there, right? And so, because of course, if there's a current I, then there's charge that's accumulating on the plates, and then that electric field then is changing with time. And so Maxwell wondered the following. He says, Faraday's law says a change in magnetic flux causes an electric field. Does a change in electric flux cause a magnetic field? Okay, so let's recall that electric flux, and I'll give the subscript E just for clarity, is the integral of S, some surface, E dot ds. Okay, and then Maxwell, so we'll define electric flux like that, and then Maxwell suggested adding a term with a change in electric flux to Ampere's law. So Maxwell suggested that we have this, not just I, the penetrating current, but E0. I guess I need an E0 here. Not E0, excuse me, epsilon 0, because this should be electric flux density, D. So epsilon 0 times this integral. So this is a change in electric flux now. So this is what Maxwell suggested, and again, here is the real current, that's the penetrating current of Ampere's law, and then here is Maxwell's amendment, I guess, and Maxwell called this displacement current. So he thought, well, maybe there's a magnetic field that is created when the electric field changes, and then that magnetic field would give rise to this current here, and he called that displacement current. So now the question is, well, does this amendment, does this addition to Ampere's law in green fix the situation that the problem that we've identified up here at point P1? Okay, well, at point P1, with the flat surface, so this thing here, at the top, this first figure that I have, there is no electric flux, right? Because there's no because our surface does not go through the capacitor. So there's no electric flux. So in this first situation, figure 1, then the green term that I've circled is 0, and it reduces to this thing. And so we get, even with the amendment here, we get a magnetic field like this at point P1. Again, no electric flux through this surface, so this integral is 0. Now, let's take a look at figure 2, right, with this surface. Now, with this surface, there's no penetrating current. Remember, there's an open top and a flat bottom. So there's no penetrating current, so the real current, or in Ampere's law, is 0. But now let's consider the second term. So if the surface has a flat bottom, then the surface area vector and E are parallel, and the electric flux is simply pi r squared times E. And so this would mean that the time derivative, r is a constant, pi of course is a constant. The time derivative would just be pi r squared dE dt. And we've said, remember up here we were going to need this in the box, dE dt is I over epsilon 0 pi r squared, so the pi r squareds cancel, and so this is just I over epsilon 0. Okay, so if I plug that into here, right, that was the time derivative of the flux, the epsilon zeros cancel, and voila. From the amendment here, I get I. This thing reduces to I, which is the correct answer. And then when I calculate the magnetic flux density, again I get mu 0 over I, or mu 0 I over 2 pi r, just like I did here, right? And so Maxwell's amendment holds in either case here, and it resolves this situation. Nice. Now, I'm gonna look at figure 3, which is the same figure, but now we can actually calculate the magnetic field inside the capacitor. Let's do that. So let's say we have, we'll take an Amperian path of a circle of radius r. Okay, we'll call this point P3. So let's calculate the magnetic field at point P3. So as we just said, the electric flux is pi r squared E, which means that the time derivative of that is just pi r squared dE dt. Okay. And so we have pi r squared, little r, times I over epsilon 0 pi capital R squared. Like we said, that's the electric field, that's the rate of change in the electric field inside the capacitor. Right? It depends on the size of the plates, which is capital R. So now, with Maxwell's amendment to Ampere's law, we get, well, there's no penetrating current, there's no current inside the capacitor, so this is 0 plus, all right, that was the real current I, plus, now the time derivative, epsilon 0 times the time derivative of electric flux, so that would be epsilon 0 times pi little r squared I over epsilon 0 pi capital R squared, which is r squared I over capital R squared, like that. So if we use similar techniques that we have been using, where we H is parallel, and then it's mu times H is B, then we have this, and we get that the magnetic flux density inside the capacitor is this thing here. So it's related to the plates, the size of the plates, r squared. It's related to how far away you are from the axis, which is little r. It's related to how much current is using to charge the capacitor. Okay? So now we can make a plot of the field strength B, which is in Tesla, versus R, which we'll say is in meters. And what we see then is that the magnetic field grows linearly with little r until you get to the outside of the capacitor, capital R. And then, as we've shown before, then the magnetic field decreases as 1 over r squared. So it's proportional to 1 over r squared, like this. So this is a plot of the magnetic field strength versus distance away from the axis of the capacitor. Okay, nice. So just to be clear here, we've tweaked Ampere's law. So remember that the electric flux density D is epsilon times E. We can bring the time derivative inside the integral by making it a partial. Inside the integral. This is a technique that we've used previously as well. And then recall that we're going to relate this to current density now to get kind of the final form of Maxwell's equation. Remember that the current density and the current are related by J dot ds, the current density dotted with the surface vector and then integrated over the entire surface. So now we can write Ampere's law like this: a closed line integral of H dot dl is equal to a surface integral of J plus the time derivative of the electric flux density dotted with ds. And this is usually the final form of Ampere's law that you'll see. So let's figure this out. How did we get here? Well, remember that J dot ds integrated is I, right? So that was that real current, that penetrating current. And then this, we've divided, there was an epsilon 0 hanging around here, we've divided by epsilon 0, so we were able to change the electric field into the electric flux density D by taking into account that epsilon 0. So now Maxwell has shown that or he's at least hypothesized that a change in electric flux creates a magnetic field. So we've got change in electric flux creates a magnetic field, and then change in magnetic field creates an electric field. Maxwell predicted that a consequence of this new, this amendment here is that radio waves should exist. Why is that? Well, the magnetic field and the electric field are now mutually reinforcing. So if you have a changing electric field, it creates its own changing magnetic field. That in turn creates its own changing electric field, and the process repeats indefinitely. So you should now have waves that can exist in free space. Amazing. And Maxwell was able to calculate the speed of such waves. So he predicted that radio waves should exist. He predicted the speed of them, which we're getting there. And then years later, the scientist Heinrich Hertz, for whom frequency is named after, actually proved the existence of radio waves. Very cool. So that's where we're going now, and I will see you in the next video. Thank you.